We're recording. We're good.
It's a bit disturbing. The combined amount of hair on this video is far less than you would expect.
I'm trying desperately bloody hard, chaps. I mean, look at this bloody mop on here.
Did you notice I've kind of tactically cropped my head just about that level?
Yeah, that would do it. Yeah, something like that.
Yeah, that's it. Look, it's better.
No.
Okay, look at this.
Look at that.
So I can't remember what vintage of Suffolk logo this is. I think circa 93, this one. Right, and make a start. We've got 36 slides, so apologies for the death by PowerPoint in advance. But we'll go through it. There's some sort of things. So from memory, those are sort of things that you need to cover in the pilot paper. So this is roughly divided up. But I seem to remember that the last section is extremely short in this. Right, so just recovering. I had this awful everything appearing at once set up. So those are the things that it certainly used to say, or last time I looked at the pilot exam paper, that you needed to know. You know, what happens on wind with highs and lows, what happens with cold and warm fronts, the type of clouds, and guessing whether high clouds or low clouds. Right, so this is the one where I always get a little bit sticky on. So this is the hardest one to comprehend for the weather, and one thing I still don't comprehend. So this may well be a wrong explanation. There is actually a video link at the end, and I will share these slides around, so people feel free to follow the links and have a look. And I found one on YouTube that seemed to be quite a good explanation. But what follows now is kind of my intuitive sort of feel for what happens. Most people talk about balls being thrown to each other and just different way of the camera angles and whatnot. This is kind of my view anyway. The bottom line that you actually just need to know is that it's actually a perceived effect, and things go and which way they go depending on the hemisphere. So we're actually on a globe. And obviously, so the fatter bit spins quicker than the narrower bit at the top, as I just said. So say we've got a high pressure up there and a low pressure down there, just in that general location, nothing to do with the arrows. You would think that we're going to have and you do, you know, the air starts moving from the high to the low. Now, this is where my explanation is possibly wrong, but it makes sense to me, and I'm sticking with it. High goes that way, but then the high has sort of moved around a little bit. This point where it was heading to's moved around a lot more. So as it's progressed down this way, actually, which way we got that? Probably got that wrong already. This bit has moved round. Yeah, let me go to the next slide. Here we go. Does make sense in the end. Let me go back. That's a good start, isn't it? Yeah, what we're trying to get your head around it a little bit is that because that's right, because if you were standing here, because you've moved quicker than if you were standing here, it looks like it's curved this way round. Can you see the mouse, by the way?
Yes.
Yeah. So because you've moved quicker, it looks like the air's gone that way. So hence it looks to get this curling motion. And the bit that I still not completely up on is, you know, how does everything then end up circulating if it's just an observational thing? But I think it's because the air is detached from the ground. I think is the bottom line. So you go high to low this way around as well. And so you end up with those sort of circulations developing. And this is a video link that will explain it far more detail than I will, but I'm still confused by it. Bottom line is you need to know which way things curve on the different hemispheres. And it's because of this relative observation effect. Everything clear as mud.
Fantastic, Chris. Okay.
Yeah, that's the hardest bit, and I should explain everything else a lot easier. Right. Oh, there was another slide there. Look, there we go. This one's a bit more fun. So this is the global circulation winds. We talk about the dead horse tropics and things as well. So because the Earth is on the H a little bit by 23.5 degrees, it's heated at this bit, and we know hot air sort of rises. So at this point here, it sets up that there's effectively no wind. The air rises straight up and goes that way, or it goes this way. And so we get these local cells setting up. Okay, so without anything, it would rise and sink at the cold bits and come back round again. And so we get that circulation system going. But it gets a little bit more complicated because of the Coriolis, and it all twists everything around. What it boils down to, you get air effectively sort of rising on the equator, falling at 30 degrees, and effectively sort of rising up again and falling at the poles. And this is where all the prevailing wind directions set up from. So this is why we get, and from here we also get our steering winds for our circulation systems. And these bits down here, so where we get the falling out, this is actually the 23.5 degree line, this 30 degree line here. And also here, these are called the horse latitudes, because in days of old, the sailing ships would get becalmed for days on end at this point on the globe, and allegedly they'd throw the horses over to lighten their load and get them drifting along the way a little bit. So hence they're called the horse latitudes. Okay, so world's on the piss a little bit, and it rises up and sinks, rises up and sinks, rises up and sinks.
Do those horse latitudes correspond to the tropics of Cancer and Capricorn?
I think it might.
Right.
But I'm not sure what the definition of those tropics are.
All right. Okay.
There might have some
I
like.
think the definition is in the summer, how far north the sun when it's directly overhead on the northern hemisphere, and the same for the south in our winter. I think those are the definitions of the tropics of Capricorn and Cancer from my geography 50 odd years ago.
That's correct. I mean, the tropics of Capricorn and Cancer is for the furthest point north or south that the sun goes. And to Paul's question, I think the answer is roughly, but actually it probably extends a little bit further than the tropics of Cancer and Capricorn lines. Yeah. So the 30 degrees is probably slightly more accurate than the 23.5 degrees line.
Yeah, and it's probably a coincidence if it is, I guess. So we now turn this on its side, and then you get these sort of cells forming. So squiggling around. Let me get rid of this jolly things, and so you get these Hadley cells forming because of those sort of rising and falling currents, and here you get these jet streams forming as a consequence. So that's what that's all about. And does anybody know? They're called steering winds, and I've never known which way round it is. Do the winds cause the pressure systems to steer, which I think is the case, or do the pressure systems move and then steer the winds? I think they're called steering winds because effectively they come first, and the pressure systems then butt up to them. Okay. Right, we're now getting on to more day-to-day stuff and more glider forecasting, but the sort of stuff I mentioned previously does come up used to come up in the paper, so have a read through about it. This obviously is a typical situation for the UK with a low pressure over it, not this weekend obviously. So what does low pressure normally mean for the UK in terms of weather?
Wet, miserable.
Yeah, wet, miserable,
Windy.
and that's quite a good thing to remember. So low pressure, wet, miserable weather in the UK. Okay, so if you can picture this picture in the exam when you come to do it, there are rules for which way the wind circulates round things, but this is, I find, more useful. So I because it will come on to it in a second, but usual weather in Britain is poor, and it's low pressure. Usual wind direction in Britain is a westerly, and so from that you can work out that, well, you can't work out, but from the rule you can work out that the wind will be going this way around the low, that sort of anti-clockwise. What's on my cheat sheet next? Yeah, that is the proper definition by Ballard's law. With your back to the wind, the low is on your left. So you can imagine you standing here, and reverse it for the southern hemisphere. But as I just said, I actually remember it by that one as well. You know, we know we have poor weather, we know we have westerlies, we know it's a low, therefore we can work out what the wind direction around the low is. Okay, now that was, as I mentioned, is at 2,000 feet. Now, interesting things happen here, and actually, certainly at Suffolk, on flying on the coast, you do get to notice this as well. So the surface wind, these two numbers are worth remembering, deflects 30 degrees over land and 10 degrees over the water. So Prize is guessing, why might we have that deflection from that ideal parallel to the isobars direction?
Surface friction.
Yeah. So you've got friction.
Friction. Yeah.
Yeah, you've got more friction over the ground, less friction over the water. Okay, so it'll be the wind here will be that kind of angle here, but it will be that kind of angle over the water. So what happens when the sea becomes water? What happens here? So when you get a 30-degree angle here, and then suddenly you get a 10-degree here.
Veers by 20 degrees?
It doesn't, well, the wind does veer, because that's, you know, the wind is now pointing along that way instead of along that way. But the wind can't suddenly sort of change direction as such. You know, if you imagine the particles are suddenly going that way, and now they're asking to going that way instead, what it actually leads to is almost like a pile up on a motorway or pile. You get do I get onto this? You get convergence and divergence. And so what you may find on sometimes you'll get to the coast, and it's not just because of the sea breeze front coming in. You could be going to the coast on a really windy day, and then you get to the coast and it's really calm. And I'm sure it's because of this difference in the interface where you go from a 30-degree angle all of a sudden to a 10-degree angle. You get the wind descending or ascending. So I might come on to that in a moment. So we may come back to that. We'll see. So actually, yeah, I missed a little point. So I pointed instinctively. The wind was moving 30 degrees in to the low here. And again, this is what here I identify it as. This is like a valley. This is like a hill. And so if you're running around the hill, going down the hill, you're going to go down into the low. So the wind deflects down into the low. Yeah, oh, it looks like it do. The vertical movement is just what I was just alluding to now. If we're sort of changing from one to the other. But we do cover it next, actually, but that's to do with convergence, divergence. Right. So equally, again, this is an important thing for the exam as well. We mentioned it's 30 degrees at the ground or 10 degrees over water, which means that as you go higher in height, which way does the wind turn?
More parallel to the isobars, so it'll be veering.
Yeah, yeah. So
more easterly.
Yeah. So you can come up with your own expressions to what happens, or you can just picture actually in your head what's actually happening. So you veer as you go up, or the way you can also remember that you back down. You back down in some things. You back.
Oh, yeah.
Backing is going anti-clockwise.
Yeah.
Veering is going clockwise. Again, terms that you need to remember as well. So actually, this entire slide, other than my slight aside on what happens when the 30 degrees suddenly changes to 10 degrees, is kind of all sorts of stuff that you'll find in the exam.
An interesting little mnemonic there for the exam, if you can't remember it, is that the word back has AC in it, which is anti-clockwise.
Oh, okay.
Good one.
Yeah. Okay. Great. So this is just, I think, what I was mentioning on the contour lines, where you're running down hills and into valleys. It's a good way to picture things. And then we'll get this area of convergence and divergence going on. I'm not quite sure why that picture's in there at the moment. This itself will come on to shortly, I'm sure, when we come on to the sea breeze front. But in general, you could see that if you've got wind arrows coming together here, you've got a lot more air at that point in time, if you like. So it's a higher pressure. Equally, where you've got the air ripping itself apart, there's less air particles there, therefore it's a lower pressure. And so sort of conversely here, we've got air particles piling on themselves here. So we've got a high pressure. And then this, obviously, this is just balances up, it's low pressure. Obviously, it's increasing to high pressure up here. So convergence and divergence going on. What have we got here? I'm not going to go through these. I'm going to go through these one by one. Right. Let's talk through this a little bit. So this is quite a typical situation. So we have a center of a low, and actually we have these fronts forming. I can't remember whether I described the origin of a front actually. So a front is obviously where one air mass is meeting another. So here, a warm front, we have, this is some warm air that's climbing over some cold air in front of it. Here we have a cold front, which is cold air being more dense, undercutting the warmer air in front of it. So we have warm air in here, and just the other side of the warm front, we've got warm air climbing over cold stuff, and we've got here with cold stuff pushing the warm air up. And here, this is where meteorologists sort of fudge things a little bit, and they say, well, it's a bit of everything at this point. So all your typical weather that's associated with this and with this, well, it can have a bit of everything in it at this point. So the reason you get these occluded fronts is that the cold fronts end up traveling faster than the warm fronts. And the origin of fronts, I'm not quite sure if I sort of cover this or not. Let me have a quick look. What we're going for while you read that. No, we haven't. Here we go. So that's, I'll explain the origin front in a minute then. So cold front is more aggressive. Of course, you can think about it, it's traveling faster. So it is going to sort of push stuff up in the air. Warm is more gradual. And what happens is that the cold effect, the effects of this cold front is going to be over a smaller area, whereas the warm front is over a much further area out into the distance. And we should cover that again quite shortly. The other thing which is interesting to note is that the wind is always perpendicular to the front. So the wind here is 90 degrees behind the front, 90 degrees behind the front here. And so what you'll find is the wind's 90 degrees here and the wind's 90 degrees here. So the wind's that way and the wind's that way. So as the front passes, it goes more clockwise. It veers as it passes. And fronts come about from those global circulation systems as well. So it's the analogy I've seen is a bit like if you sort of gloop some jam or something onto the poles of the Earth. You can imagine that sends a whole ripple of jam across the Earth, and it gets swept around in these sort of low pressures, high pressures, if you like. And so this is the result of air splodging down on the poles. Can't recall whether they've got a better diagram than that, but that's where it comes from. That's where these fronts come. You also then get troughs as well, which is the results of high altitude pile-ups of these global air movements. Talking of air movements as well, and we do have a section coming up, I've just noticed on the next slide, showing the typical weather associated with these. But we get these types of air as well. They just get classified. So the air mass itself, there's 4 basic types. And it describes whether they're typically dry or wet, cold or hot, or a combination thereof. So you get continental polar airflow coming sort of from Siberia, and that will typically be cold and dry. You get maritime polar air, so that's going to be cold and wet. You're going to get maritime tropical air coming in this way. That's going to be hot and wet. I always got this one coming up here as well. So depending which way it comes from, affects the it affects the soaring for nothing else, because again, there's a lot to cover through this, so I'm trying to rip through this. It affects the density of the air, if nothing else, and also it will affect the sort of lapse rates and how aggressively the thermals shoot up in the air. Because if we've got colder air, like today, we've got really cold air, there's big temperature differentials, stronger thermals. So the types of air mass do affect the type of weather we experience. Types of clouds. I'm just going to click through onto these ones here. As I'm mentioning, warm fronts, they stretch over hundreds of miles, whereas cold fronts are a lot sharper. The cold fronts basically equals thunderstorms, heavy showers, and warm fronts every other sort of drizzly, manky weather that you get. And again, what I'll do, I'll just circulate these decks afterwards to pick the pace up a little bit. Next slide we've got here. These are the types of clouds. So these are the sort of things that you're expected to understand in the pilot exam as well. It all comes from your Latin, but you can kind of figure out which one's which from the descriptions. So you've got alto is sort of like mid, so mid altitude is alto. Cirro is kind of like high altitude. Cumulus obviously is fluffy. Lenticular is sort of wave shape, and stratus is sheet like. And so I guess this is the only sort of really sort of weird one. So sheet-like cumulus, stratocumulus is where you get a layer of fluffy stuff, and altocumulus is when it's a little bit higher. Altostratus is where you've got a layer of just thin cloud at mid-levels. Nimbostratus, it's raining. Nimbo being rain. Cumulonimbus being our thunderclouds and our anvils going on here. And we will actually come on to hill fog and things shortly, as well as rotor cloud. Skipping on again. So this is the sort of stuff that we've covered over here, and it looks like I've got a bonus question coming up. Haven't really covered a lot of these, but does anybody know what relative humidity is?
Yeah.
You like to say?
All right. Yeah. It's the ratio of the current atmospheric humidity against the dew point of the air, which is 100% humidity.
Yeah.
So you know,
yeah. It's the percentage of the air's capacity to hold water. Dew point being what it is. And the air can hold more water the hotter it is. Hence why when things start going higher and start getting colder up there, we get clouds forming, because they aren't as well. The air can't hold that water; it has to condense out, and it also get some latent heat and some other effects going on. Now, this is interesting. So I'm asking you questions for stuff we haven't sort of really covered yet. That's very good as well. So there's 4 different ways in which clouds can form. Does anybody want to guess what they may be?
Being raised, cooling.
Sorry?
It's being raised and therefore cooling as it goes up with height, therefore it condenses.
Yeah, there's 2 of those. Any others?
Well, there's,
Katabatic. No,
yeah,
where it goes up over a hill and condenses at the top.
Yeah.
where it touches a cold surface.
That's interesting. That one's not on my list, annoyingly.
Because
Yeah.
essentially fog is ground level
Yeah.
cloud, isn't it?
Yeah, you're right, actually. I mean, that's probably the fifth one in which clouds can form. But yeah, so you've got widespread lifting. So this is kind of like your warm front. Orographic is, like you mentioned, going over the hill. Convection, fluffy clouds. Turbulence as well is kind of an interesting one. I guess things can be kicked up. I think it's probably a bit like scud cloud, probably is an example of that, maybe, or scuddy cloud behind hills, perhaps. But yeah, advection where it cools on cold surface and condenses out is another one. Right, so this one is the most useful to you day to day out of all of the weather stuff. And it's the sort of stuff that we can look at. And this is what RASP does for you automatically. But I would recommend that you start looking at the soundings on RASP. So if you go to RASP table, in the I think it's on the drop down or it's on the menu, you'll see somewhere to go soundings, and it defaults to Exeter, and it likes to keep defaulting back to Exeter. But there is a sounding for Cambridge, and actually there is another way you can go custom soundings for exactly where you are in the world, and custom sound or within the RASP region, and that's the real world example of what I'm about to talk about now. So this is what the syllabus says you need to do, by the way. So this is what you need to do is what the syllabus say you need to go. So, and that's what we're going to go. We've already talked about veering and backing. We're going to sort of talk about some of those other terms as well. Tetrograms being another one. And yeah, high and low pressure. Well, we sort of covered some of that already. Thermals, fully understand convection. So yeah, trick question, why do thermals rise?
Because the density reduces,
Yeah,
relative to the surrounding fluid, which
Yep.
is the atmosphere.
Yeah, they rise because it's less dense, not because they are hotter. Hotter obviously tends to equal less dense, but it's actual density that makes them rise, the density difference. So less due to the temperature, but then this is an interesting one as well. So on their own, if you were to heat up, I mean, you see this all the time. You've got a hot field. The sun typically heats the ground. I think only 10% of the sun heats the air or something like that. Most of the air's heating of the air comes from the ground being heated up and then that warming the air above it. But we've just said that, okay, I'll go for the hot air rises, the less dense air rises. But what's to stop that layer of warm air suddenly rising up and then dissipating and not giving us anything to play with? What actually happens is nature is quite handy in this, in that nature abhors a vacuum. If it was to suddenly rise up, there'd be a vacuum underneath and it'd be immediately pushed down again. So you do get this situation, which is slightly counterintuitive, is that you get this less dense air sat on the surface of the ground, not going anywhere. Because if it was to go anywhere, it'd get pushed down again, because you've got a vacuum immediately done. And so what you need is some sort of trigger to effectively burst this bubble, this upside down bubble of air. And that's what we get for a trigger. So this is where your tractor comes in, or you've got this layer of warm air and the wind is sort of blowing it towards a tree line or a hedge line. And that gets a little bit of rotor and that just pricks this thermal. And so you get this feeder of warm air on the field and rising up in this column at the point you've got the trigger. You also get things like cold water can act as triggers as well.
So is that why when the farmer's out, harrowing his field, that's what kicks the thermals off?
Absolutely, yeah, because the air on itself will just sit there. So if you got some, and the other one was Nick Chitty, famously at the Worlds a couple of years back. He was chasing Ollie, and Ollie was getting quite low. Nick ran around like a crazy fool in the fields just below where Ollie was, and kicked off a thermal. And then Ollie climbed out on that and then did quite a lot better in the task.
All right.
Not completely convinced that's in the rules, but you know, it wasn't excluded from the rules.
Didn't Judy Ledden have that in Australia when a herd of sheep stampeded? And they kicked off a layer.
Quite
I
possibly.
think she had.
So in addition to winchmen, marshals, we need field tramping wallers, really, don't we?
Yeah, go on. But then once you've exhausted your feed, that's it. You know, you only get the first few lucky pilots.
All right.
Right. So the next one is how strong is the thermal going to be and how high is it going to rise? So guesses at what this is?
Well, it's the adiabatic lapse rate, dry adiabatic lapse rate versus the environmental lapse rate. The difference between the two is the energy.
Yeah, more fundamentally, you're just looking at the bigger the difference in density or heat, if you want to think of it that way, is what we tend to think of stuff in actual. The more energy you're going to get. So the bigger the temperature differential, is what it boils down to, is the stronger it's going to rise, and it's going to keep rising until, well, sort of until that density equals out, so the temperature equals out, which is relating to those different rates that we'll talk about in a second. In reality, there's a bit of inertia, so it'll probably go a little bit beyond that. And there's also sort of effects where our cloud starts condensing out. It's releasing heat and warming stuff underneath it. So things don't quite, you find it a bit more difficult to actually get to cloud base. So you could be 100 foot underneath it. Exceptions being cunims of stuff, of course, when it's really strong. So how strong is it? Depends on temperature and humidity differential. Right. Some terminology I'm going to run through now. So lapse rate we just mentioned, and that's simply the change of temperature in height. And there's various numbers you need to remember, and I get a little bit confused with them as well. We'll see them in a minute. You get the environmental lapse rate, which is the average, and you get the dry one where there's no moisture, and you get the wet one where there is moisture, saturated and dry. Obviously, we'll come on to those in a minute. Yeah. So the environmental one, that's the average. That's if we're a uniform, not the Goldilocks sort of thing. Nothing's really going on. That's what we're seeing. The dry one, so this condenses, this cools down quicker when there's no water in it, and then you get the saturated one, cools down slower when it's got water in it, because as that water's cooling out, it's going from gas into liquid, and so you are releasing energy. So you're going into a less energetic state, and so that's also then warming the air. So that's why the wet stuff cools less quickly, because it's condensing out into liquid. And here we've got the numbers. So I guess there's sort of nice round numbers there. These ones you do need to know. So without anything condensing out, it's 3. Saturated is about half that, and the standard giving is about 2 degrees. And in the other ones, there's other numbers that are important to know. The standard atmospheric pressure, which is also the code on the gate at Dunstable.
Yeah, it is, isn't it?
Although it's out by 1, it's not in the middle. It's on the edge. 1013.2 millibar, and that is the agreed zero height for sea level on average, basically, for the average sea level. And this one's important as well, because there's some varied calculations as to what happens if the pressure changes, gets more, gets less. So every millibar is roughly 30 feet in height. So it's also useful if, like me, you were designing altimeters once upon a time as well. So if the we'll come on to that. I'm not going to confuse it now, just looking at the time. But 1 millibar is a change of height of 30 feet. And obviously, the higher up you go, the lower the pressure. So you can kind of work out that if we're 30 feet higher, the pressure's gone from, say, 1,000 millibars to 999. Go another 30 feet higher, it's then 998. So there are some questions on this, usually in the exam, but it might help you to just write a few little examples just to picture which way's up. Looks like I've got a story now. Here we go. I'm probably going to skip over this because I should probably just go straight into the diagram, but you can read this later. Right, so this is a simplified tephigram. So this actually is a tephigram, which is otherwise known as a sounding. So the soundings, which you see on RASP, are actually two lines. They are the temperature with height, which is the red line, and there's the relative, I think it's absolute humidity with height, which is the blue line. For now, this effectively, we're just looking at the red line, and we'll just take it for granted where the dew point is on this diagram. So this here, this bold line, this is effectively our temperature with height. So when they send up the weather balloons, this is what they're measuring. So as you get away from the nice warm ground, obviously things cool down and they cool down and they cool down and cool down. And then what quite often happens is the air starts warming up again, and then it starts cooling down again. So any guesses why the air might suddenly start warming up at a certain altitude? We covered it earlier briefly in all air movements and things. Is
it like that congestion you're saying with the what do you call it? Diversion and convergence.
Yeah, it's potentially like this. So you'll see on high pressure days, you'll get an inversion forming, and that is, you know, air descending on stuff and stopping things rise up. So effectively, it's trapping a layer of warm air up here. Another thing you may see on this is you may see a temperature inversion if you've got a warm front coming in, a warm front moving. Obviously, that wouldn't necessarily be a thermic day because this will all be grey cloud up here, but warm front's another example. But yes, high pressure days you get inversions, and they are quite helpful, as we'll see in a minute. So what happens is this is the air here. So the air temperature is normally about this really, but we're warming up our nice fields, and then we get triggered off, and this is the temperature of our little particle. It gets triggered. This is now going to cool because it's nice and dry at 3 degrees per 1,000 feet. It's going up here. It keeps cooling, keeps cooling, keeps cooling, keeps cooling. At some point, it reaches dew point, at which point it starts condensing out, and it then starts cooling at half of that, at 1.5 degrees, and it starts cooling and cooling and cooling and cooling and cooling and cooling, and then it then hits the inversion, and it can't go any higher because they're the same temperature. I'm talking temperatures now, not densities, because it's easier. And so this is the cloud top, this is the cloud base. This line here, what rate is that line representing?
2 degrees per 1,000, isn't it? Yeah, LR.
Yeah, it's the environmental lapse rate.
No.
Yeah, and this here, oh, I think my comment was slightly wrong. So the other thing that may happen is, obviously this line, I think I initially drew this way around. So what can happen is, especially on a hot summer's night or hot summer's day, you get the ground cooling down. And so we said that the main mechanism for warming the air is the ground warms it, but equally the ground's also the bigger thing that can cool stuff down. So you've got the air touching a cold thing, it's going to cool the air immediately above the ground at night. So what you get ground inversions where at night or first thing in the morning, because the ground's cooled down and cool down this early layer of air, you'll actually see a little inversion here. And then as the day warms up, you know, maybe gets back to sort of late morning, you lose that low down inversion, and then you start heating up, and then we're going to get this is just our field's heated up and it's been triggered now, and off it goes. Okay, so any questions on that?
Is there a dew point rate?
So there isn't a dew point rate. That just depends on conditions. There is a way. I'll see if we get a bit of time to,
Right.
so we can show you on RASP.
All right.
This actually looks like and where the dew point comes from.
All right.
But there are various hidden lines on, not hidden lines, guidelines on RASP, and they all relate to these lapse rates. Oh, incidentally, what would happen if we didn't have this inversion in this example?
it'd become unstable, wouldn't
Yeah.
it? The cloud would keep going up and up and up and up.
Yeah, there'd be nothing to stop it.
Yeah.
So
like
with that,
monster.
yeah, you get QNIMs. So,
Yeah.
and you can see here that the saturated, that this is, it's diverging from the environmental rate here. So it is. So this is our unstable conditions when saturated rate is we're cooling great. Yeah. So which way around is that? So the environmental is cooling greater than the saturated. So this is 2 degrees. That's 1.5 degrees. If the environmental round here wasn't its average, you know, maybe that was cooling at 1.5 degrees, maybe that was only cooling at 1 degree for some weird reason, then it'd be stable. This is going to converge anyway at that point in time. But unstable, yeah, there's nothing to stop it. So the saturated rate is, so we're cooling at less than the environmental. Oh, yeah, so that's correct. So it's accelerating. Right, got some notes. Forecast soundings. So this is just a summary of what we've covered so far. And again, I'm going to have to skip over this in the interest of time. Things we haven't mentioned are things at the bottom, anabatic and katabatic. So anabatic is going with airflows up something, and katabatic with airflows down something. Anabatic, I remember in a fairly crude fashion, based on the 3 initials. I'll let you work out what that might be. So that's anabatic is going up something, and then you work out what katabatic is. Weird one, which I always give the answer for because it's terrible. I hope they removed it from the latest papers, which is CAVOC, which you never use, and it's, you meant to remember this acronym, which is on. Did you encounter this in any of the microlight stuff, Charlie, when you were doing your PPL? No, Charlie's still with us, probably not. Yeah. But anyway, ceiling and visibility okay, and it equates to this. So you need to know that it equates to 5,000 feet and visibility greater than 10 kilometers, because after all, we use it every day gliding. Okay. Flicking on thermals. Again, there's some descriptions of typical air pressures here. I'm not going to read through this. I'll let you read through this afterwards on the notes. I'm just wondering, actually, how do I get the notes to everyone? I might just put a link on all of the places. I'll put this on, people can grab them. Okay. So you need to be able to describe the typical weather. You kind of probably can work that one out for yourself. You've lived in the UK long enough. So this is what we've covered. Life of a thermal, lapse rates. I will definitely make time to come back to those soundings at the end. Local effects. Okay, we should be able to flick through this. This is on slide 2436. So I want to flick through this quite quick. These are the things that we need to understand. It's more hill, so it doesn't affect flatlanders, although also sea breezes and sea breeze fronts, of course. We've talked about some of this earlier. So this is probably more relevant if you're flying in the Boss or you're flying in the Alps and things. So why would valley winds not be the same as pressure winds? In fact, in France, they give 2 winds. They give the meteo winds, which are the higher up winds, don't they? And I can't remember what they call the winds, lower down winds. Why do we get differences in the winds from the pressure system winds?
I suppose because of the topography and the fact that it's actually channeling the air or directing the air into the along the valleys.
Yeah, exactly. Yeah, so one of them is funneling of winds, and also you get the things like the Föhn winds and the whatever, the Mistral is where you get the pressure systems at either ends of the Alps on a big scale pulling stuff along the valley systems. But you get this locally as well. And the other reason you may get that is the heating of the slopes. You know, so if the one end of the valley has got a south-facing slope and that's heating up, then the air is going to flow, you know, during most of the part of the day towards that hot slope as it gets pulled along and up that slope. And then it's probably going to reverse at the end of the day when it goes into shade and goes back the other way. There's an awareness that things will change. And we've got an example here. This is actually talking about Yeah, I'll just click through all of it. So this is our anabatic wind again. So big mountains rising up, so the valley winds sort of drawing up to it. This is quite a rubbish diagram, actually, I noticed. But you can pick, if you imagine this is a closed valley, it might be the easiest, and it's following that way. We get nice clouds on here, and at the end of the day, everything collapses, and it all just reverses here, and we pushes up and get a nice magic lift. But yeah, local effects. Sea breeze. I think we kind of all know this, really. Land heats up, hot air rises. You kind of need to know where's the low pressure and where's the high pressure as well. So that circulation system I showed earlier. So if I was to point at this bit here, would that be high pressure or low pressure at this point?
It's high pressure.
Yeah, yeah, high pressure thing, which makes that
low pressure.
Yeah, low pressure. Well, it probably makes that one
low pressure.
It's sort of high pressure because you've got things pushing into it. Because this is then low pressure because it's going up. Got the circulation.
Oh, yes, you're right. Sorry. Yeah.
So
I get it.
That's fine. So that's the basic things. And this is continued. So I've got some other diagrams. In fact, there we go. That's what we just pointed at here. And there's another nice little diagram nicked from somewhere there. So this is the famous sort of sea breeze front and the curtain cloud where things get dragged down. You need to get for a sea breeze front to form, you need to have something to form against. So in Suffolk, if you've got an easterly wind, the air's already moving that direction. So there's no conflict, you don't get any front. You'll only get a front if you've got opposing wind, so southwesterly or westerly or something, going against the direction of where that air is going to move in, and they then do that.
All right.
So don't ever sort of fall behind the sea breeze front. What type of air is here? So
sinking air.
Yeah, sinking air, cold
air.
Cold air. All of the nice bubbling, all of the potential, all of our nice little thermal feeder pools have just been swept aside by this cold air. Yeah. So there were no thermals in the immediate aftermath of a sea breeze front going through. And so you get lots of things descending from here. So you fly through the sea breeze front, you're going to be on a glide into the deck. So what you need to do is stay on this side, so that's down the land side of the front. Also, I think you tend to find this might be sinky here, but just beforehand. So always look to have some good height. Don't go on a blind charge and think, oh, I'm going to get up, because what you'll probably do, you'll end up flying through here and just ending up in some sinky bit here and landing. You want to be aiming to land, get to the sea breeze about there. And it's quite a good little reference to release. There's an old release article about there. I can sort of send around links to the release magazines if people are interested. Wave. So again, we sometimes actually see the effect. We feel the effects of this in the flatlands perversely, but you feel it more directly, obviously, in hillier places. So wave is where simply you've got a sandwich of air. This is not quite correct. Well, I always thought it was, no, actually it probably is right. So we get an unstable layer of air and a stable layer just quenching stuff, and it's all a bit springy. So the air comes, it starts bouncing over this one, and it's a bit Goldilocks. It's just right. The wind strength's just right, and the atmospheric squidginess is just right, that it happens to like just coming up at this point here, and it sets into its natural oscillation. And so the next time it comes, it's like pushing a kid on a swing. If you push at the right point each time, you'll get them higher and higher. And so if you've got your mountains at just the right spacing, you will get this rising large area of air. So here's all going up, here's all sinking. Here you want to be, here you don't want to be, and you definitely don't want to be around here. And we've got some rules for what is needed to start the atmosphere bouncing. And in Suffolk, we can actually sort of see something coming across the North Sea at times. Right, only 7 more death by PowerPoint, and we can do a quick bit of RASP within the time. What am I covering here? Yeah, this is a local one here. No idea whether that link still works. Wave isn't always good. You kind of need to do dealing with. I crashed in quite stupidly on top of Stanwich once, but I was basically being stalled all the way along Stanwich Edge. I was being like a dolphin. It was quite horrible and scary. And then hence I put in this little rule that the local pilots used at the time. Okay, this is where actually we touched on earlier. Different ways fog can form. Different ways things can get cold. So by cooling, by moist air coming in, sea fog, which is very similar, I think, to advection fog, isn't it really? So, or the other way around, warm land to cold sea. And hill fog, where it's forced to climb over. Things crawling out. I guess advection, these terms you will need to know a little bit in the exam. In fact, most of this you kind of need to know in the exam, which is why I've highlighted these bits specifically. That's what we've covered. Right, synoptic charts, last bit. So we're getting some last practical bits. This is what you need to be able to do. You need to be able to read those synoptic charts. So I'll show you another weather link as well, and you can practice that. Obviously, you can get those on the Met Office and all sorts, but I'll show you a cheaty place to get it. You need to be able to link cloud types to precipitation as well. So I think, again, you can probably figure that one out. But that'll be saying, you know, what type of, are you going to get precipitation with alto cumulus? Are you going to get it with nimbo stratus, nimbo cumulus? You'll find the clues in the name, which is the nimbo bit, for example. And that's what we need to know. The other thing you need to know is they're not actually synoptic charts. That's a different type of chart, but we call them synoptic charts, I guess because everyone's been calling them the wrong thing for a while. They're actually isobaric charts. So it's showing lines of equal pressure, isobaric, a bit like isothermal, same thermal, and so forth. Here's an example chart. So let's have a quick look at it. You can see how old the 2005. Can anyone remember? Was it a good year? So if I'm sort of, I don't know, sitting south of my geography's poor, is that Greenland there? Or was it Iceland, Greenland, one of them? What's the weather likely to be here? Do we think? What's the
warm front? And
yeah,
sort of high to low.
So you got warm front, yeah, warm front's good. So what type of what type of is it sunny? Is it cloudy? Is it wet? Is it dry?
I think it'll be
getting cloudier, isn't it?
Yeah. I think it's cloudy.
Increase in cloud as you get closer to here. And what happens to rain as well as you get closer?
Yeah, more likely.
Yeah, it will increase. It's not a case of likelihood, it will increase, you know, as you, well, assuming this is not an old weird thing that's all you spent out, it will increase as you get closer. What about sort of the wind speed? Is it windy or not windy here?
Not very, because they're quite spaced apart. I mean, they're like, those isobars are like half, you know, a quarter of the UK length.
Well, that's I'd say that we're reasonably close together, but actually there's another bit here which I haven't told you about. So here we're about 60 degrees latitude. There's a key up here, so 60 degrees latitude. Oh, we haven't covered latitude and longitude yet either, haven't we? 60 degrees. This is quite hard to read actually, but for this spacing, you can read off in knots. What's that? Something interval. It does tell you how strong the wind is going to be. But the other thing that isn't terribly clear, and I don't understand the reason why, is that the winds around high pressure systems are greater than low pressure systems. So you need someone like Rebecca Sherwin to sort of explain why, but that's sometimes you'll see some isobars and look reasonably spread out on the forecast, and you'll go, well, that looks a light wind day, and then you realize it's quite windy, and the reason being, one, it's a high pressure behind it, and the other thing I think probably happens as well is if, you know, so you've got all this, you've got all these winds coming in here, they're not suddenly going to stop. They're going to keep going for a little bit as well. So you've got to remember that, you know, this is just what we're seeing here is the pressure system, which is sort of accelerating, I guess, and driving the wind. But if you've got, you know, lots of wind coming in anyway, it's not going to suddenly stop just because the pressure system isn't driving it as much. So wider spacing, windier. As you approach, you know, these, the warm front is going to get wetter. Here it could be any weather. This is actually an old front. Look, it's turned itself around. This is an old front as well. This is not a particularly good chart, but here, where's a classic thing? We've got troughs here, so they're basically like cold fronts. And that's the result of atmospheric pileups. And this is a cold front coming in. So we're probably going to see storms here. This here as well. What's the weather going to be like here?
You got, well, it could be anything, couldn't it? Because you've got a cold front followed by an occluded front.
Yeah. So what's probably happened is we've probably had lots of big showers just clearing through. There might be a, if we're lucky, there might be a momentary glimpse of sunshine before all this horrible murk comes in and drizzle. Yeah. Yeah. So you can read a lot from the charts, and it's really good to see charts and not just look on the computer prediction, because it shows you the general scenario of what's happening. So you're not at some random point in the model. So you'll, all the sort of people like Steve Blackler will do that, and all the top pilots look at the charts as well. Summarization of what type of rain's associated with things. Again, I'll send it around for people to look at later. So perhaps do a bit more interesting. But cumulonimbus, have a guess what we're gonna get type of precipitation.
Well, it's flipping thunderstorms and stuff like that, isn't it?
Yeah, lashing down.
The big old monster ones and hailstones and things like that.
Yeah. What about alto stratus?
Not
No, yeah. No. Alto is the mid-level cloud.
Yeah.
The high stuff up. Don't care with it. And stratus is just sheet cloud. Alto cumulus.
Just going back to the previous one, is that where you would get that virga? You know, where it sort of like just rains, but it doesn't actually hit the ground. Is that?
No, that's a lot lower. It's in the lower layers. Alto stratus is like 15,000 feet or something.
Oh, okay, all right.
I think it was on that previous diagram I skipped over.
Oh, okay.
An alto cumulus, similar. Is it going to rain? Not rain?
I don't think it's going to rain.
No, there's no nimbo in the word.
No.
Large cirrus.
No, it's ice.
Yeah, it's true. Yeah, cirrus are going to more likely to be ice crystals, but it's not.
That's all right.
Yeah, you might get some of those mare's tails where the ice crystals descend if you're at like 50,000 feet or whatever they're at.
Yeah.
Okay, so that is the end of the death by PowerPoint. So what I'm just proposing to just do now is hopefully I can kill that, and instead, hopefully without sharing anything confidential. Otherwise, yeah, it's not too much on that. You're fine. What I want to do is have a look at a couple of quick things quickly. I'll only spend like 10 minutes on this. Appreciate the time. I'll jump the gun a little bit there. Right. So this is my website, mycloudbase.com. A very few little things on here, including tracker, of course. A few things, blah blah blah. I still use this myself because I have this handy page of all the weather links. So here is my weather links page, and you see I've got the BBC weather and I've got the XE weather. I tend to look at this for weather. This is for wind strengths. I know Paul likes windy, or is it windy, one of them. But we're looking at the weather properly today, so we're interested in these up here. So there's the synoptics. I'll let you have a look at these later on here, but these are just all of the latest. Just always check the dates on the charts. So yeah, that was midday today. So we can see, you know, high pressure in charge, nice, big, massive high pressure, which we fully expect to be in charge for a few days, giving us some nice, pleasant weather. But I don't know if you've noticed, we should see a bit of an inversion on the charts, as we've mentioned earlier. What's going to happen? What's going to happen here again? What sort of weather we're going to get if we were there?
It's going to be murky. We're going to get
Quite
lots
windy.
Yeah, very, very windy, very murky.
of.
It's probably more. Yeah, this is a boring chart at the moment because obviously we're under this big ridge of high pressure, so it is definitely great for flying. But interestingly, look, we
You're
can
going too fast, mate. You're going too fast. Get back to Thursday. That's when we're going out.
we can see that by Saturday, if this chart's correct, if it happens, Ireland's going to start getting some drizzle and some rain, and then it looks like it's going to get probably a large range of showers coming in here, and the winds are going to be picking up. But we're probably still quite all right on Saturday. Still, we've got this nice little ridge of high pressure, but it's probably still the same scummy air that we've had for the last week. So it's probably going to be quite murky, and looks like this will come through at some point in the early parts of next week. Interestingly, when we're looking at the charts, the next 2 days are going to be reasonably accurate because they get looked at by humans in the Met Office. So the next 2 days are pretty much good. Anything beyond the next 2 days is the computer's best guess. So that's where it comes, but it's not too bad.
All right.
But have a look at that. That's michaelairways.com and the weather. I recommend you sort of do that as part of whenever you check the forecast and start associating it with the charts.
Is that link? Is that link on the code? Suffolk Coastal Floaters site.
Don't think. Oh, it might be possibly. There are some links.
I've got a feeling I've seen that.
It might well be.
All right.
But the one we're just going to show quickly here is RASP Stratus. So this has obviously moved around since Paul Polska passed and is no longer with us. So he's now hosted here. And you've got various things on here. Interestingly, there's things that people don't use quite a lot. So this one's quite good, by the way. This is Blip Spot Maker. And this one, I haven't been on this site for a while. Let me just pull in. We haven't got. We must have something for Cambridge here or something. Cambridge South. Generate. Right. So this is a blip spot. You can do custom latitude and longitudes on these, but they've got some predefined gliding club turn points, and you can get on here all of the charts, what's happening on the day in one page, which is quite nice. So this is what Cloudbase is doing, and thermal strength and all the rest of it at Cambridge. That was today. All right. As the day progresses on, this is what the temperature is going to do, surface and upper winds, wind direction. So it's just a nicer, sometimes, way of checking what the weather's going to do. But always, again, look at the big picture. Always look at the big picture, because it could be just some little blip on the model. But that's a blip spot maker. And I say I don't know quite how we do specify specific. Oh, here we go. It's coming soon. But you probably find Mendlesham will be in here specifically, because that is one of the turn points. Yeah, there you go, Mendlesham. So we could go for Mendlesham on Thursday when I've moved my day. And so we're expecting, what's that? High to critical updraft. We're expecting to be getting up to about nearly 4,500 feet. It's going to be reasonably breezy, because this is in knots.
Yeah.
So RASP thinks it could well be blown out. So hope not, but we'll see. We can look to those charts, and that's what I'm saying. When you look at those charts, the spacing was quite wide, and you think, well, theoretically it should be light winds, and that's the answer for the exam. But in practice, there's stronger winds on those charts. So if we have a quick look, go back at Thursday. This is what's going on here. You think, where are those winds coming from? and I don't know is the answer. In theory, there should still be quite light winds. But maybe it's, all of this So it's really windy around here, and maybe this is just keeping going. Right, that wasn't what I was going to show you. I was going to show you some tephigrams. Right, on here, this is the normal RASP you look at. And you switch to full parameter set, and yeah, there's a lot of stuff you can look at. Up here, you'll see you've got some called soundings and also custom soundings. So custom soundings, I suspect you can, again, you could probably get one for Mendlesham, or soundings, I know Cambridge is in here, but it defaults to extra all the time. But let's have a look at custom soundings, because I bet Mendlesham is under here. Yeah, Mendlesham. And we're going to go for Thursday at, well, let's get for 1:30. Is this going to work for us? Yeah, so it's gone off and it's calculated it for Thursday. Now, does this look familiar, hopefully from the slides we saw earlier?
Yeah.
Right, the thing to do is ignore all of that top bit. All you're interested in is like the bottom couple of inches here. VASP actually gives you a little bit more information. So it actually gives you the wind speed with height in this green line as well. The wind direction and the little barbed arrows. It usefully adds like a little gauge of what the height is in thousands of feet. Normally a tephigram is just in terms of pressure. So you only see this bit normally, but RASP is nice. It helps, and it gives you the correlation from the pressure to the altitude here.
All right.
The other thing it helpfully shows you is, so this red line, that's our lapse rate. That's our environmental lapse rate. So that EALR figure is just an average. In reality, it's probably going to be something like that. That's I'm not quite sure that is 2 degrees per 1,000 feet. Actually, it is, because that's this line here. That will almost certainly be our environmental lapse rate here. All these grid lines. So all of these lines help you plot stuff. I think this helps you plot the saturated, how things condense out as well. But we see, assuming now a little bit of, so this is our temperature here. The air temperature is 10 degrees. Now, let's just say that the air near the ground is only warm to just a bit above 11 degrees. It's going to be rising up to here, cooling at 3 degrees per 1,000 feet. So, yeah, so that's 3 degrees per 1,000 feet. So it's cooling at 3 degrees per 1,000 feet. This little dashed line is actually showing you what's happening. It's doing that work for you. It's doing the sums for you.
Is that the 3 degrees per 1,000 feet? That dotted line, the dashed line. Is that what you're saying?
It happens to be, yes, because
All
these
right,
solid lines are 3 degrees per 1,000 feet, and what this dashed line is the path of the thermal.
All right. Okay.
That's showing you the path of the thermal, because it's helping you out, and
Yeah.
it's showing it's once it starts rising, it's going to rise at up to about here, and then you notice something happens, and then it starts actually the rate of cooling halves, and it starts curving like that, and it stops here. So what do you think's happened here? At
The cloud form, the base of the cloud.
Yeah, base of the cloud. So that's it. So base of the cloud is about 4,000 feet, or just under, and cloud tops are going to be 8,000 feet. So you can immediately see that the clouds are about 4,000 feet in height on Thursday. Now, why is that kinky bit there? Well, this here is the dew point. It's the absolute humidity. I think or is it the dew point? I think it's actually the dew point, which would probably equate to pretty much the same thing. But the rule here is, see these dashed lines? If you follow that dashed line up, you'll find you hit where it starts curving round. So, so you take that bit, you run it up to here, and that's where your cloud base is.
Yeah.
You run it up that dashed green line.
Yeah.
I should actually make that. Can I make that bit bigger? There we go. Make that a bit bigger for people. There we go. Because after all, that's all we're interested in. So if you run it up to here, it's then starting to cool around. And yeah, so that's what we're going to see. Now, you can imagine what happens if, for some reason, you've got a patch of a field's got really hot, but for some reason it's been baking in the sun all day. That could get up to, I don't know, maybe gets up to 15 degrees before it goes. It's going to be a bit of a rocket. So what's going to happen is going to be a lot further away than the atmospheric, and remember that the strength of it is related to the distance between the air temperature and its temperature, and it's going to cool at that rate. So it will start condensing out here as well, and then cloud tops may well be 10,000 feet.
Can I just refresh on that? Is the red line the ELR?
The red line is the actual air temperature. It's the real thing.
All right, okay.
The EALR is just a model. It's just an average.
Yeah.
So what we're now seeing is this is real life.
All right, okay.
And so you can see that tomorrow's Thursday is going to be quite safe. We're not going to get any QNIMs, because even if the temperature was to get up to like 20 degrees, it's probably going to start condensing out. It's still going to stop and hit this line at 14,000 feet. So it's very unlikely to be QNIMs, certainly at half one.
Yeah.
If I click, I should probably go around forward in time, or I need to dial. So let's have a look at 3 p.m. instead, see what's happened at 3 p.m. If you choose the actual pre-done sounding, this actually is a lot quicker because it's pre-calculated them.
Mm.
There we go. Right, so now pull that in. And actually that looks pretty much the same, doesn't it? There's not an awful lot changed in the two. But it's interesting as well. Have a play with these soundings on days where there's thunderstorms forecast and or normal days. If I ever go back to some standard soundings, let's go for Cambridge. I wonder if we can do. Let's go really far in the future. Let's go for Monday. See, it keeps resetting to Cambridge. See, so here's another example. So Monday, it thinks that cloud base can be 4,000, but only small little cumulus. Look, because it's got this little lip.
Yeah.
And when you actually something you'll see this line and the red line kiss at some point. So this where it is a dew point. Come to think of it, so it's where the dew point and the temperature meet. You're going to get a layer of thick cloud. You're going to get stratus, and RASP helpfully shows this on the side as well. Normally we'd do these sort of weather lectures. It's usually autumn or winter, and there's a lot more interesting weather going on. But it's a fine day at the moment. So we've got this period of good weather for a long time.
So am I right in thinking if you haven't got the scale for the height, it does have it though, doesn't it?
It does, yeah. It's over here.
I was going to say if you knew the local pressure at ground level, and then you do 30 millibars per 1,000 feet, then 1 millibar per 30 feet, then you could work out the height as a result of that, couldn't you? From the fact that it's 850.
Yeah, but I definitely commend. Look at the synoptics. So look at those charts and compare them to the forecast. Also, get in the habit of always checking out the soundings, because it will tell you a lot about the day, not least about how cold it is. You can see here that it's going to be. This is next Monday, and everything's warmed up lovely. You know, at cloud base, it's a balmy 8 degrees. But if we selected today at cloud base today, it was about freezing.
Yeah.
And I think we looked back earlier when when Gordon abandoned his flight. You can see, I think I measured like he was predicting -6. I think he recorded -15 in the end at cloud base.
Richard, actually, I think it's colder than freezing, isn't it? Because if you've got the zero line, there, it's actually going up diagonally to the right.
You think this line is the temperature as well?
Yeah, it's a skew chart.
You're right.
Standard epigram.
You are, yeah.
So you come down here, so it's -8.
If you look, you've got 10 here, 10 down the bottom there where your pointer is, and then go up to the right. There's another 10 up to the top right.
Yeah.
I'll tell you what these diagonals are here. That's probably the environmental. But it's good to look at these. But yeah, thank you for that, Charlie.
And there's another one on that chart you were showing. I can't remember if it's this one or the previous one, but if there was a sign of high level cloud, high level stratus, which actually might tend to kill some of the thermic activity up at about 20,000 feet.
Yeah, there was something on there. I didn't point out
on the Monday one, I think. Yeah.
It's a really high level this is like cirro cloud happening at 25,000 feet.
it's not that thick on that chart, so it's probably not going to do much in the way of killing the thermals. But if that was a solid, thick blob all the way to the right, you know, to where your arrow was, then it could be killing the thermal activity.
Yeah. And you get also you sometimes hear this much lower down here. Like if these lines, like I said, did touch, you would certainly see cloud forming here. So there's so much you can read off these charts, especially what RASP adds to it for you. So look at the general position, look at RASP, more than just the pretty patterns, although they're good for a quick check. And then you can see it's really useful to see how things change as the day goes on. If I click on this, and here we go, look. So this, now we've got this layer of cloud coming in. This is at, so this is next Monday at 4 o'clock, say. Who knows what's going to happen? And then the cloud's building, and you see the cloud base is dropping. And what you may find is this is possibly associated with some front coming in even. Maybe it's a warm front coming in, I don't know.
So is the black line on the left-hand side near the 850?
There.
Is
That's
that
representing cloud water here.
Oh, okay. All right.
Yeah.
So what's that?
Equally, Richard, aren't on the right hand side there? Haven't you got the wind direction changing,
Yep,
indicating
absolutely.
that it's that we've got a front coming through?
Yeah. So you've got here, yeah, good spot. You've got the winds. Now, what do we say? We said you back down, you veer as you go after the front goes through. It veers, doesn't it?
Yeah.
So, is that what we're seeing here? Because
Quicker at height than low down.
Yeah.
It's going clockwise as you go higher.
Yeah. So this is at 1 o'clock. You click through, it's veering. There we go. There he goes. And it's veered. So yeah, so that's the front going through. So there's an awful lot you can read from these and what gets added. And interestingly, you can get an idea of what the upper wind strengths are as well. So.
Can I ask on the diagram that shows the wind direction, the direction of the line,
yeah,
is essentially let's say for example
that way. Your point is that
is that saying essentially the wind is going from, well, what's that? That's 80 degrees. Or is it saying it's 270 degrees?
It's saying it's 80 because you got the little winds, these little barbed at the end.
All right.
Reflects the wind strength as well.
All right. Okay. All right. Okay.
I think is it 1/2 knots or something? There's some sort of rule.
I think it's the Beaufort scale. So a half is 1 on the Beaufort scale. A full line is 2 on the Beaufort scale. 1 1/2 is 3, etc.
Yeah, there we go. So you've got these lots of. So the wind's blowing that way.
Right. Okay.
Which way, Richard? So if you look at 4,000 feet for this particular chart,
yeah,
are you suggesting that the wind is from the southwest or the northeast?
Southwest, west-southwest.
I thought, yeah. So it's pointing in the direction away from the barbs, in other words, like it was an arrow.
Yeah.
Okay.
Yeah, that's it.
It's interesting. I've seen it more than a few times where people will just focus on the stuff in the middle. And if they were to pause for a moment, I realised it was going to be a crap day because it's blowing about 40 knots.
Yeah.
But everything else is alignment, but we just gotten the wind speed. Question of looking out the window.
See this being, and like there's some big kink up here or something. And sometimes on towing as well, because this is 2,000 feet, you could see it increase quite dramatically with height. And you go, well, it's going to be fine on the ground, but it's going to be really, you can be up and down on the winch tow, or that's no good for tugging or whatever.
So interesting question. Would that, what's showing there, would we be able to aerotow with that sort of wind strength?
Hold on, it's a wind strength on the Beaufort scale.
So here, well, we've got you could use this, or you've got this cheaty line. So the wind speed is here.
20 knots.
Remember that when we're aerotowing, the thing we're most worried about is what's the 10 meter to sort of what is it, 30 feet up to about 300 feet, because that's where it's likely to be roughest if the wind is strong.
Yeah. I mean,
and this would suggest this is not going to be aerotowable at that time of day, because you've got some residual thermic activity, and it's too strong near the ground.
Yeah.
But winching would be fine.
Yeah. And I've seen some very dramatic ones of this reaching up to here.
All right.
Okay. So that's just one wanted to run through. So we've gone over a little bit. I thought we might do on this one because this one's a chunkier one, and I've been racing through. And the weather's more the sort of thing you actually need to sort of ponder on a book and read through. But we're kind of like ticking that you've had a bit of a lecture, and actually hopefully that's provoked a little bit of thoughts. You can go and read up what I've got wrong and correct yourselves. There's quite a lot of resources. I'll send these notes around.
Is there an official book for the pilot exams and everything?
Yeah.
Or
The BHPA's pushes, is it the BHPA pilot handbook?
okay.
Yeah, I can't remember which one it is now though.
Yeah. I mean, it's definitely worth getting. I used to have, when I did this, I got it used to be the Microlight Pilot's Handbook was the thing that you got. That's obviously quite outdated now. BHPA did their own thing, so which is the BHPA Pilot's Handbook.
Pilot handbook, yeah.
Yeah, I'm sure it's a Pilot Handbook. The other thing that you can do is, obviously, if you're interested in the weather, you've got things like that, which is Dennis Pagan's Understanding the Sky.
Is that one as well, Richard?
Exactly.
Alan Watts, Writer's Weather. That's quite an old one, but it's good.
Yeah.
I've got that one.
That one's in the PDF now, actually. So
Yeah.
yeah, Air Riders Weather. So yeah, it's always been, it's always been more accessible than others. And in these days of YouTube, I'm sure there's a whole heap of series on weather that you can get. Yeah, that's the one.
Von Bradbury's book is reckoned to be absolutely excellent.
Yeah.
Yeah.
Meteorology and flight.
I think the great thing about this subject is that, yeah, you can learn enough to pass the exam, but actually there's no harm in continuing to learn, and you can just keep continuing to learn for the whole of your life.
Yeah, there we go. I mean, one of the other things that I looked at, even the micrometeorology, I find quite interesting. I haven't looked at that for a while, and that's difference in surfaces between, say tarmac and brownfields and light brownfields and trees and forests, and so trees absorb heat during the day and they let it off slowly in the evening, so that's better for thermals at the end of the day. And also I think even just silly things like a ploughed field versus a smooth field, and differences in color and temperature and all sorts of like little things kicking on the
Nuances.
Yeah. I guess someone like Taka would be the expert on that as well. So Taka, who will source a molehill from 2,000 feet in the fens.
Brilliant. Well, thanks, Richard.
That's all right. No, thank you for your time.
Very much
Thank you. Appreciate your time and doing all that.
That's okay.
Yeah, what they say about you, you are a good old boy.
Well, I tried to.
No, they don't know the truth.
All right then, guys. Thank you very much. I'll stop recording, and hopefully it's recorded, and I'll
Thanks, Richard.
circulate it around.
Brilliant, mate.
Ping the link.
Cheers.
Cheers all. Bye bye.
Thank you, Richard. Be safe, mate. Be safe,
Cheers,
all.
guys.
Bye, everybody.